Okay, so we're doing transformation of variables, change of variables, transformation of variables. He gives you a region, an integral. It's not that nice. It's doable, maybe? You'd have to do two separate regions, upper curve, lower curve, chop it up. It might be doable, but he wants you obviously to use change of variables. He gave it to you. Sometimes they don't, but here they give it to you. And so we're going to convert all of this to u's and v's. It'll have the region being transformed, meaning these vertices will be transformed. The integrand will have to be converted to u and v, but fortunately x plus y is equal to u, so that'll just be u squared there. We'll have to include a Jacobian, and then do the actual integration. Okay, so the Jacobian, it's a function of u and v. A lot of times it'll come out to constants. When they're linear transformations, it'll be constants. But in theory, it could be a function of the two variables u and v that's included in your integral that you're going to jam right there. You need dx du, dx dv. The order doesn't matter technically. And then what you're going to include in there is the absolute value of the Jacobian. dy du, dy dv. Just the combinations of all the partial derivatives. But they are x with respect to u and x with respect to v and so on, which means that you need to rearrange these equations and get x equals in terms of u and v. You gotta eliminate y or x. So let me start doing that. The x's are ready to be eliminated right away, so let me do that one first. I'm gonna add them straight away. You get u plus v on the left is equal to 3y on the right, and I want to solve for y. Y will equal to u plus v over 3. That's one of the equations. And I'll be able to get my dy du and dy dv from that, but I need to also go back to these originals and multiply that one by 2. To eliminate, negative 2. Negative 2, negative 2, and then negative 2 there. I'm going to multiply that first equation by negative 2. So that my y's will cancel, and I'll just get x's in terms of u and v. The y's cancel, I get negative 3x is equal to negative 2u plus v. And I'm going to divide by negative 3. Oops. Sorry, my color scheme. I'm going to be consistent. So I'm going to get negative 2u plus v is equal to negative 3x. And then I divide by negative 3, and I'll get x is equal to, it'll change the signs and have a 3 in the bottom. So it'll be 2u minus v. Okay, I'm ready to do my Jacobian. It's going to be, and this is a determinant, and so it's going to be dx du. Where's my, right here. And it's just a coefficients. I wrote it like this, but it's 2/3 u minus 2/3 v, 1/3 u, sorry, 2/3 u minus 1/3 v, 1/3 u plus 1/3 v, so they're all just those third coefficients. dx du is 2/3. dx dv is negative 1/3. Watch your signs. Dy du is 1/3, and dy dv is another 1/3. I'm doing the determinant, so it's going to be 2/3 times 1/3 is 2/9, minus, and that's negative. 1/3 times negative 1/3 is negative 1/9, and so it's going to be 3/9, which reduces to 1/3. That's my Jacobian. Again, in theory, it's a function of u and v. That's a function of u and v. It's just a constant function, but be aware you can get u and v in that when you work it out. Okay, we are ready to I didn't do my region. I'm going to save the work here for my actual integral. I'm going to transform the region here by probably taking all those coordinates, 0, 0. I either take the vertices of this and transform them, or I take the curves, but the bounding curves, and transform them. I did discuss that in a previous video. The simplest thing to do here is do the vertices. It's not always what, sometimes you have to do the curves, but here it's not going to be too bad. I am going to do this mentally though. I don't have space to work out the details, but this is, let me organize this. Keep track of variables, don't confuse x and y with u and v, so these coordinates here are x and y coordinates. 0, 0, 2a, comma a, and a, comma 2a. And that's a picture there. It's more accurate than his picture. His picture has a weird scale, and it's not shaped accurately. His 2a that way is not the same as 2a that way. We're going to transform it to u and v. And again, I'm going to do it mentally. X and y, x is 0, y is 0. That's u is going to be 0. V is also going to be 0. Okay, x is 2a, y is 2a. When I add them for u, it's going to be 3a. When I subtract negative 2a plus 2a, it's going to be 0. And then when I transform that one, x plus y is going to be 3a also. And negative x plus 2y is going to be negative a plus 4a, 3a. And the idea is these are supposed to be, I mean, you're picking these transformations from x and y to u and v, or he's giving them to you in a way that is supposed to make this region easier to integrate. So a lot of times it comes to things that are vertical and horizontal lines. Let's draw it out and see what we get. This is now my u and v axis. It's all in the first quadrant, so it should just show the first quadrant. U and v, and then let me mark off. We got a lot of 3a's this time, so there's 3a, 1, 2, 3, 3a there. Okay, and I got 0, 0, 3a comma 0, and then 3a comma 3a. So it forms this right triangle where one of the sides is a nice vertical line, and that makes it easier for us to integrate. It's going to be a lot easier for us to integrate this. He doesn't give a name to this region. Some books will call it S. You transform region R to region S, just a different letter. It is a U and V region now. And now we're ready to rewrite this integral. And I'm going to do it over here. Got to put all the pieces together. Let me copy it down first. A is just a constant in all these contexts. A is just a constant. No, I don't want that. I mean, yeah, you know that. Okay. Oops. Okay. I'm going to rewrite my integrand in terms of u and v. So I can look at that x plus y and know that's equal to u. But if you don't if it's not something that's boom on the board like that, you can work it out the longer way, which is to literally substitute x, whatever x was, right here. 2u minus v over 3 plus y, u plus v over 3. So it doesn't have to be something clever like, oh, hey, right there, it's going to be u squared. You can literally use that. Put 2u minus v in every x there. Put u plus v over 3 in place of every y there. Simplify it though. Don't leave it like this and start working with this. Obviously this simplifies. Talking to you, Carolyn. Alright, but anyway, we're going to simplify that. My Jacobian, do not forget that. That is an absolute value of the Jacobian, 1/3. That is just still going to be 1/3 obviously, but it is the absolute value of that. I believe. Don't double check that. Then I have my choice of doing du first or dv second or vice versa. So now I have to start thinking about how I'm going to do my region. As for now, I can just put S and dA, meaning integrating over an area over the region S, but I will have to break it down. And that means I got to look at equations. I got to figure out these functions. I don't have time to go through it, but anyway, this one's going, your slope is 3a up, 3a over. That's a slope of 1. It's passing through the origin, so this equation, v is like y, u is like x, and if this were a rectangular, it'd be y is equal to 1x plus 0, or y is equal to x. That's your diagonal line. It comes up a lot. Make sure you can just recognize that as a diagonal line. And also make sure you can rewrite it in terms of v and u. It's y is equal to x, except it's u and v's. Okay, but if you could have like a slope there. So your new form is going to be y is equal to mx plus b, except with u's and v's. So again, the transformation will often translate things to nice, simpler lines, but you have to be able to give those equations of that line using your linear stuff, slope and intercept form, point slope form, whatever you got to do. Anyway, that's my equation right there. I'm probably going to do it the usual way, which is to slice this way. I pick a random x, and I'm going to do with respect to y first, so I'm going to go from there to there. Okay. So with respect to y first, that's my y, and my upper curve is y is equal to x, and my lower curve is y is equal to 0. Except I'm using v instead, so it's just doing the same thing, but again, v is like y, u is like x. Then I'm going to be doing with respect to u. So then I got to do all these slices starting from here all the way down to there. So u is going to go from 0 to 3a. Okay, I'm going to pull the 1/3 out from there. I'm going to simplify this, and I get 16a squared plus, and when I simplify that, it's a common denominator already, but if not, you will need to add with a common denominator. When I add them with the common denominator, it's going to be 3u over 3, because the v's are going to cancel. So that's how you get u. Don't forget that squared. It is just u squared, and that's what we got to do. That's going to be, that integral will be equivalent to this over that region. So that's the benefit of it, is it made it a lot simpler. Your bounds are simpler. It's not these two separate regions that you'd have to do. Your integram's a lot simpler. Note that you are integrating with respect to v first, so you're not trying to do any kind of fancy thing with the u. If you were integrating with u, that would be a trig substitution situation, but it is not. We're doing with v first. So let me start working this out, but get a good look at that, because I got to make some space for me to do the work. I'm done with this because I've already transformed it, so let me just erase this. And I've transformed that, so I don't need that anymore, and I'm going to finish up the problem over here. Okay. Alright, let me just copy it down. Okay, with respect to v, there's no v's here. This is just a constant when we integrate with respect to v. So just like when you're doing integral of 3dx, your antiderivative is 3x. This is going to be that constant. This is my 3 constant right there, times v. That's what that is, constant times the variable of integration. I'm evaluating that from u to 0, and then I'll be doing du after the fact. And I will also not forget that 1/3 there. All right, plug it in u, and then plug in the 0 just gives me a u. So my first layer of integration gives me that. That's a result of integrating with respect to v first. Now I have to do with respect to u. And now it is not trig substitution. It would have been trig substitution here. If you were working with u and all you have is a u squared under the radical. And so you do have the choice of, when you get to the situation, you do have to think, is it going to be better to do v first than u, or u then v? So you have to use that knowledge of switching x's and y's when you did that. Same thing applies here. It may be better to do it u first than v, but not. That would have been trig substitution. This is going to be regular not u substitution. It's going to be regular substitution, so it'll be cleaner than trig substitution, a little bit easier. I can't use u substitution because I already have a variable u, so I'm going to use w, but same idea. Let w, that's usually what they go with if you can't use u. It's kind of, I've seen it multiple times, but whatever letter you want, your favorite letter is fine. I'm going to let w equal that. My dw is going to be equal to u du. That u and that du will become 1/2 dw. Do I want to change my bounds of integration? Yeah, why not? Okay. When u is equal to 0, my w, I'll show my variables, is equal to just 16a squared. When u is equal to 3a, my w is equal to 16a squared plus 9a squared is going to be 25a squared. Okay, so now don't forget the 1/3. I'm going to be doing w goes from 16a squared to w goes to 25a squared. I do like to write those. You've probably noticed that because I do like to keep track of what variables, these values are for what variable. Where am I at? I got a radical w, all of that under the radical, and then I got a 1/2 dw. Almost there. So again, the u du is equal to that. My whole integrand is equal to w. Okay. So I'm going to get a 1/6. I'm going to pull that out here. I'm going to do the power rule on that. That's going to be w to the 3/2 over 3/2, so it'll be 2/3. And I just have to evaluate that from 25a squared, 16a squared. And these are somewhat nice because they do have nice square roots. And this 3/2 power is a square root and then cubed. You're on your own for that. I don't have time to go through that. I got other problems to work on. So review, we've gone through it before. So make sure you can do 3/2 power. It's a square root cubed. So what am I going to get here? 1/9? Yeah. Okay. And then I'm going to have 25a squared. And then I can write out what I was saying. So again, 3/2 power is the 2 on the bottom makes it a square root. But then we will have to cube it. Same thing here. It'll be square root. And then we'll cube that, and the whole thing will be to the 1/9. Sorry, multiplied by 1/9. Okay, so you're going to do square root 5a, cube it, 125a cubed. Square root that, 4a, cube it, 64a cubed. Over 1/9. And then, what is that going to be? 61. Yeah. Over 9 a cubed. I believe that's what I had last time. So if I've done everything correctly, that's your answer, and I was careful this time, so I think I'm good. And I had the same answer as last time. Alright, I'm going to post this